So welcome to our today seminar by Xaver Mooslechner. He is presenting turbulence models and how to implement these turbulence models in NGSolve. So welcome, Xaver.
Thank you. So hello everyone from my side. Thank you for joining. I would like to welcome you to my today's talk about turbulence modeling in NGSolve. And I will give you a short introduction about the different simulation principles for incompressible turbulent flows and how we adapted them and applied them in NGSolve in our FEM framework. And I also will show you some results from my master thesis. So firstly, I would like to give a short outline about my presentation. It will be separated in 3 parts. So firstly, we were going to define and characterize incompressible turbulent flows. Then the main part will about those 3 main modeling principles. And we will have a short insight into the theory and also in the application in NGSolve. Yeah. First, I would like to try to start with the introduction. So how do we define or characterize turbulence? This is by no means a very easy topic. So it is basically described by its characteristics in contrast to laminar flow. So turbulent flows are chaotic, which means that in the sense of very small disturbances in the initial field and with a flow with a very high Reynolds number, those perturbations or disturbances start to amplify and will lead to the so-called laminar turbulent transition and lead to an uncorrelated flow field. This makes more or less a deterministic approach very impracticable and intractable. So a fully description of the flow in motion in space and time is often not desired. Turbulent flows are also unsteady. True stationary solution, or the true stationary solution does not exist due to its high irregularity. Turbulent flows are also rotational, so turbulence only arises and persists in rotational flows, so in the presence of shear. And they are also very diffusive, so such flows cause a very rapid mixing of any transported quantities such as momentum or heat. And turbulent diffusion also allows a much faster mixing of any quantities than molecular diffusion. And in the end, it's also a very three-dimensional phenomena, which can, especially in wall-bounded turbulent flows. As you can see here in the figure, what is very crucial here that turbulent flow, or in the regime of turbulent flow, a wide range of different length scales to exist. So we have really big energy carrying large eddies, and we have some more independently behaving small noisy eddies, which are more dissipative. And we can mainly divide 3 different approaches to numerical solve and compute turbulent flows. The first we will explain is the run simulation, which is called a Reynolds average Navier-Stokes simulation, where we try to model all turbulence scales. So there we do not resolve any eddy or vortex or something else. So here the main goal is to find a kind of time or averaged or mean value of our problem, of our quantities. And herefore we have a very low computational costs. On the other hand, the direct numerical simulation, the DNS, really tries to resolve all relevant scales. So from the Kolmogorov scales, which are the smallest ones, the very dissipative ones, up to the large scales, which are very dependent on the boundary conditions on an autoflow and so on. The problem here is that we have a very high computational cost. And in between there is the Alias and the VMS. So here we try to kind of separate the larger scales, so the lower frequency modes, from the smaller ones. And here there are 2 different approaches, the Alias, VMS, we will see that later on. And therefore the computation costs are quietly reduced in contrast to DNS. In this figure, I kind of tried to show you a comparison between those three approaches. So we have here a velocity signal. So the DNS would represent all scales. The Alias would only kind of show you a filtered signal, so only present, in this case, a low pass, the low frequency modes. And in this, for a time signal, of a signal over time, for steady rents, the rent solution would be a time averaged quantity, so a constant in this case. Yeah, so firstly, I would like to start with rents, shortly talk about the theory, and then we go to some examples. So the, as already mentioned before, in rents, often or in many engineering applications, exact description of the flow or of the flow quantities is not desired. So we need a kind of a statistical description. And Osborne Reynolds was probably the first who occupied this topic. So he introduced the so-called Reynolds decomposition and Reynolds operator. And this decomposition of the flow quantities in its mean value and in fluctuating part for the velocity as well as for the pressure. And generally, this mean value is defined by this ensemble average, which is a Reynolds operator. Historically, also an ensemble is a collection of notationally identical experience. Since flow is turbulent, each fluid motion, or this has some historical aspects behind, because there, if you repeat an experiment and some small differences are happening in the experiment setup, this will become very significant as time progresses. So we have a completely different flow regime after time progresses. So an ensemble average would be the average of all those identical experiments. But we can say also for ergodic systems, so that we have an instance of each ensemble for a very long time period can be considered as a representation of all possible instances. So that means for ergodic systems, the time and ensemble average of physical quantities would be equivalent. Nevertheless, we just see, we don't know which kind of time averaging or averaging it really is. So we define our Reynolds operator by these certain properties. So it's with its linearity, it commutes with derivatives and with constants. And if these conditions are fulfilled for this operation, averaging operation, then it follows that we also have these properties that, for example, the fluctuating part, the mean of the fluctuating part would be 0. However, what we are going to see in the next slide, fluctuations moment or statistics moment of second order are not necessarily 0. So if we apply this Reynolds operator and the decomposition into our Navier-Stokes equation, we derive the so-called Reynolds average Navier-Stokes equation, which can be seen here in this set of equations, which are almost the same as the incompressible Navier-Stokes equations, except there is one additional term which comes from the convective term, which is the so-called divergence of the Reynolds stress tensor, which can be seen here. And now we come to, or we lead to this famous closure problem of Ranz. So we have about 10 unknowns, but only 4 questions. So this Reynolds stress tensor has to be modeled in some kind in order to close our problem. And here are 2 different ways to do that, or to model these stress tensor. The one more common way is to use these Eddy viscosity models. So therefore we use an analogy between the gas kinetic and the turbulent processes and so on. And the other way would be to have these so-called Reynolds stress models. There we would try to solve for each component of this Reynolds stress tensor and transport equation. But here the problem again is that we have many unclosed terms. So there we have to model again. But the more common ways to use these Eddy viscosity models, and in this talk we will basically focus on them. So the Boussinesq hypothesis is based, as already mentioned, on this analogy. And the assumption is that we set for a Reynolds stress temper is kind of proportional to an eddy viscosity and to a mean strain rate, which is defined here. And what is going to do in all those turbulence model or eddy viscosity models is find a way how to determine this new T, this eddy viscosity. And if we have that, we can close our problem. And here again, we have many different models. There are algebraic models, quite restricted to very easy flow scenarios. We have the one equation models like the Spalla-Dalmaris model, and we have more sophisticated models like the two equation model. A very famous one is the K epsilon, K omega, and K omega SST model. In this presentation, I will just focus at the K epsilon model since they are quite similar all. So in the K epsilon model, the eddy viscosity is determined by this ratio. So we have the turbulent kinetic energy squared divided by the dissipation rate and some constant C mu. And this turbulent kinetic energy and its dissipation rate has to be solved by those transport equations we see here, which are modeled again, which they are not the exact equation of for turbulent kinetic energy. There are some terms which are unclosed again, and which had to be modeled. So here we have our material derivative. Here we have some production terms. So these equations are quite similar. Here we have our destruction term, and here we have molecular turbulent diffusion. Also, in the existence of any solid walls and boundaries, there are mainly two different ways how to incorporate such boundary conditions. The one is called the low Reynolds number version, where we really try to resolve or to sufficiently resolve our boundary layer. And the other one is where we use wall functions at the nearest cell at the wall. For example, for the velocity or for K, we use some specific functions there. So since we now know how to mathematically model a turbulence model, we need a few other things in order to numerically solve it. So we need an appropriate discretization method, we need initial boundary conditions, we need a time stepping scheme, and so on. So yeah, just let us have a look in NGSolve and how we do that there. So yeah, I tried to keep it quite simple. I provided or prepared a file for this case. So here we are going to simulate turbulent flow over a backward facing step with the use of an K omega turbulence model and run simulation. So first of all, we have to define our geometry and our mesh setup. So in this case, we used a structured, stretched quadrilateral mesh. So we are able to set our geometry and can also define how many cells we want to have in each direction and to set our stretching parameter, which is then needed for the generation of our mesh. We also define some flow properties. For example, here the kinematic viscosity, which will be 10 to the power of -4. And also the turbulent intensity and turbulent length scale, which is then important for the initial values of K and omega. So if we do not have any previous state where we can load from, where we just have to load the mesh and the grid functions, we will generate our own mesh, which is comes from or returns from this function, which can be seen here as well. So here we define all of the mesh points, then our elements, and so on. So yeah, let's have a look how this domain does look. So here we have our mesh on our computational domain. So as already said before, we have our backward facing steps. So we have here an inlet boundary, here an outlet boundary, and those all are solid walls, no slip walls. And here's our backward facing step. and we have a better finer grid in the vicinity of those walls, and especially at the corner. So if we have our mesh in our geometry, or we are able to define our finite element space for the Reynolds equation as well as for the turbulence model. So for the Reynolds equation, we use the HDiff conforming HDG method. Therefore, we have the HDiff space in the tangential facet FA space for our velocity and a normal L2 space for pressure. Here, all those three spaces are incorporated in a new one, and then we define our test and trial functions. In this example, we use an conventional H1 confirming method for a turbulence model. So we just define it with an H1 space and also define our test and trial spaces. We can also have examples where we have an HDG formulation for our turbulence models, which can be seen here, where we have an L2 space and a facet FA space, which can be also done here. So then after that, if there is no state loaded, we have to define our grid functions, one U, K, and omega. And the velocity would be the first component, pressure would be the third component, and so on. And then we define our damping functions. Since we are now using a low Reynolds number version, what I explained before, so that means we try to sufficiently resolve our boundary layer or the region at our walls, we need some damping function for some of our terms. I won't go too much into detail in this. They are quite highly nonlinear functions, but we just have to implement it as a coefficient function and use it then quite straightforward. So then we define our eddy viscosity, which has also a damping function multiplied, but the original function would be just a ratio between the K and omega. After that, we set our initial and boundary conditions, which is also quite straightforward. So as we have an inlet velocity boundary, we define a laminar parabolic velocity profile there. If there is no state loaded, we set them at the inlet mesh boundary. For K and for omega, we use initial values from this formula. So it just should act as an initial gas for K and omega. And if we have the solids, at the solid K would be 0, solid walls. And for omega, we set it to 100 or 1000 or to a higher value. Then we draw everything. And then we are finally able to define our bilinear and linear form for the Reynolds problem. Since we have this HDG formulation and we try to approximate U piecewise polynomials on elements and additional polynomials on facets. And since by definition of this method, we have a normal continuity, we need some extra term in order to force tangential continuity. So here we would have the integral over each element. Here we have this new term in order to get our tangential continuity. In order to have consistency, we have to symmetrize, and or to have a penalty term as well. Here we have the Stokes, just the bilinear form for our Stokes problem. Therefore, we neglect or we do not incorporate the convective term. So we have our pressure gradient as well as our incompressibility constraint. And here we also use a small hack, since we have a saddle point problem and this 0 pressure block in our matrix, and we want to get rid of it. We use this extra constraint and to get rid of it. And we will later explain how this has some computational advantages. For our convective term, we have to define our upwind velocity. So if we have an inflow boundary, we have to use the facet tangential velocity or phase to variable. And if we have an outflow, we use the one from the element, which is then defined here and here at the element boundary. This is one integrator over the element. Then we define our right-hand side as well as a residual vector. And in order to get an initial velocity field, we just solve our stationary Stokes problem, which is done here. And I would like to show you how does it look like. Take some time. So this would be our initial velocity field, which should just act as a kind of velocity as a guess, which doesn't seem very correct. And for k, as already said before, we have this initial value all in the whole domain, except at the boundary we have 0. And the same thing basically also for omega, where we have a really high value from 100 or 1000 at the boundary. So after we have our initial and boundary conditions, we just continue with defining our bilinear form and linear form for our turbulence model, which is also quite straightforward. So for our A matrix, we define firstly our convective and our diffusion term. And in our A matrix, since we are using for the Rans equation and for the turbulence model, this IMAXing time stepping technique, we treat all terms implicitly except the convective term and the sources in terms for the turbulence model. So here we do it for K, also for omega. And then we define our production term, which is then needed for our right-hand side, since it is a source term. There we have our destruction term. Then we sum everything up and use it in our right-hand side. The same thing basically also for omega. Here for this specific K omega model, we also have kind of a cross diffusion term, which we also treated explicitly. So after that, we just define our time step size, which is in this case 10 to the power of -3, and then define our bilinear forms for time integration. As already mentioned, we are using this IMAXing time stepping technique. So the M star matrix consists of our Stokes problem times the time step size plus the mass matrix. And the same thing also for the for K and for omega. Then we define our start time, our end time, and the corresponding inverse matrices. Since we now have a symmetric problem and we got rid of this 0 block, we are able to use the Sparks-Kolesky solver to have a better computational, better compute in parallel. And then if everything is set up, we are able to enter our solving loop, so which will end after the end time has reached. The first thing what we are going to do in each iteration is always to update our right-hand side. So in this case, our convective term for the Rans equation, since the velocity changes, and also for the K and omega equation, since K and omega is also changing as time progresses, so we have to reassemble these right-hand side linear forms. And then, since also nu t is no constant anymore, not like in the Navier-Stokes where we have the normal kinematic viscosity, which stays constant, here we have a variable which really depends on our flow quantities. So since then, we also have to reassemble our A matrix and our M star matrix. And in order to kind of save some, or to get save some time, to be not that time demanding, we use here a matrix vector addition, since they do not differ quite a lot. And since M star or updating matrix is getting exchanged, we also have to solve our linear system again or update our inverse. And in the last part, we do the real updating. So we update U, P, K, and omega. So we add up our residual or right-hand side, and then use the updating algorithm. And if it's necessary, we can also have a VTK output. And if the simulation is done, then we can also save our state. So let's have a look how the simulation does work. So here we can see the velocity. It's quite slow, really, really slow, but anyways. So then we may have a look at the eddy viscosity, how it progresses as time. So here we would have the eddy viscosity, which is calculated by this ratio of the turbulent kinetic energy and omega, the specific dissipation rate. Here we would see the turbulent kinetic energy, which also changes as time progresses. And yeah, that's omega, which is obviously very high values directly at the border, at the solid walls. Yeah. So after many, many time steps, we would then achieve some kind of converge to a stationary point. Okay, I will quit this and we're going back to the slides. So here I prepared some two cases, what we have seen previously, the backward facing step scenario. What here the difference is that we have a laminar case, laminar flow with a Reynolds number of 500. In the bottom one, we would have a Reynolds number of 10,000. That would be a turbulent flow. And here we can clearly see some differences. So in the laminar case, we have a really big circulation bubble behind our backward facing step, and also a second one at the top. And for a turbulent case, the recirculation bubble is way smaller, and the velocity is far more spread into our domain behind our backward facing step, which is quite nice, I think, is the one with the periodic hill. Here we have periodic boundary conditions there and there, and constant pressure gradient, which kind of drives or forces the flow. And also, as before, we have one laminar case and one turbulent case. So here we have a Reynolds number of 500. The one in the bottom is one with 10,000. And here we also see some very significant differences. So for the laminar case, we have two recirculation bubbles, and the flow does not really kind of enter the valley and kind of goes above the hills. And for the turbulent case, we have only one recirculation bubble, which is closely behind our hill, and the velocity field is much more spread and also more going into this valley down and then also up. Yeah, the second topic I would like to introduce is Alias and VMS. So as already mentioned before, in Alias, the basic idea behind that is that you separate our scales. So you really try to only resolve the largest edgy, which depend on our boundary conditions and our outer flow, and we try to small these more noisy and dissipative words. In order to do that, we have to kind of separate them And in contrast to RANS, in Alias, we are using a filtering method. So in this case, it would be a low pass filter. And we decompose our quantities into a large and small scale part, which can be seen here for the velocity as well as for the pressure. So here we would be the filtered velocity signal, here would be the remaining one. And this filtering operation is defined in this equation. So we have a filter convolution kernel with a filter width and our signal. And there are different kernels such as Gaussian kernel and top-hat kernel or sharp Fourier kernel. But mainly this filtering operation has to satisfy a set of properties which are quite similar to RANS but not the same. So it also has to be, this filter operation has to be linear, commutes with derivatives, and with constants. And also this implies that these kernels are bounded. And this filter operation, which is quite a very crucial point, I think, it is not a Reynolds operator, since if you filter this small scale part, it would be not necessarily zero. And here I kind of tried to show you a comparison between different filter kernels and in time and spectral space. So here we have the unfiltered velocity signal, and here we would have the filtered one, where we have some difference between the top hat and Gaussian filter, and here we can also see it in the frequency domain, those different filter kernels and how they behave on this signal. So if we apply this operator, this filtering operator, Alias filter operator, onto our Navier-Stokes equations, we obtain those so-called spatial filtered Navier-Stokes equations, and which can be seen here. So we have basically the same equation as in the incomplete Navier-Stokes equation, but one problem: it commutes with those derivatives, but we do not know how to treat this filtering operator onto this multiplication. So we have a very a similar closure problem as in RANS. This does not equal, so the filtered of the product is not each filtered quantity times the filtered quantity. So a very common way here to address this issue of closure is to introduce the so-called subgrid scale stress tensor, which is the difference between those two terms. And this tensor T, in this case, has to be modeled. Here we use also a very similar assumption as in RANS before, since the small scales are very dissipative and the main task is kind of to extract energy from the larger scales, from the more kinetic, more energy carrying scales to and convert them to heat. This can be also accomplished by this Eddy Viscosity model, where we have more or less the same equation as for RANS. So we have a proportionality to a subgrid scale viscosity as well as to this filtered strain rate tensor. But the big difference now is to RANS is that we have a way smaller range of scales which has to be modeled. We do not need a very sophisticated model like a two-equation model or one-equation model, since we only resolve a bigger part and only model a smaller part. Therefore, algebraic models like this Magarinsky model, which can be seen here, are for most cases quite sufficient, and this filter width can be computed there with this geometric mean. There are also sometimes in Alias, or if you start to do any Alias computations, there are some things which are quite confusing. That's the way how to treat this subgrid scale model. So I would say there are basically three different ways to do that. There is the implicit Alias, which also ILAS. Therefore, the filtering is implicitly provided only by the discretization and by the grid. So we do not take any model. We just use we also talk about coarse DNS. We just use our Navier-Stokes equations and use an under-resolved mesh, and therefore the numerical diffusion or this truncation error would act as a subgrid scale model. So this is also a very common way. The second more common way, or the most famous way, is the implicitly filtered Alias. There we try to numerically solve our filtered Navier-Stokes equation with an appropriate subgrid scale model, what we have seen before numerically. So that's is very, very similar to runs, what we have seen before. And a very uncommon way would be the explicitly filtered Alias, where we really explicitly use a numerical filter on our equations at each time step. And here I kind of prepared two video animations of an Alias of a turbulent channel flow at friction Reynolds number 395. I will explain later how we calculate this turbulent Reynolds number. These two simulations do only differ in its resolution. So we have one with a more coarser mesh, one with a more finer mesh, but the initial setup, the initial field, and the boundary conditions are all the same. And what we are going to see here is this chaotic behavior also for turbulent flows, that firstly the coarser simulation, the mesh simulation with the coarser mesh, will have an earlier start of the laminar turbulent transition process than the one with a finer grid, and also the how the flow progresses as time progresses will be quite differently. So let's start the video. So in the upper one, we see that it's getting quite unstable, reaches more faster the way to turbulent. In the bottom one, it seems completely differently. It takes longer. And in the bottom one, in the top one, we have already reached the fully turbulent mode. And then after some time steps, we also reach it in for the high resolution case. In VMS, we have basically the same idea as in Alias, but the scale separation is defined in a different way. So here we use the weak formulation of our Navier-Stokes equations, and a scale separation is then defined by this variation projection into the appropriate subspaces. So firstly, we define our spaces for velocity and pressure. So we assume our boundary contains Dirichlet and Neumann, homogeneous Dirichlet and homogeneous Neumann boundary conditions. And then we obtain our weak formulation, which can be also written in this short form for our saddle point problem. And then we decompose our spaces and functions into three parts. One is the large, the small, and the unresolved scales, which can be seen here also for test and solution functions. And if we insert these three scales or this separation into our weak formulation, we obtain a system of three variational equations, which can be seen here. So one equation for the large scales, one for the small scales, and one for the unresolved scales. And since we are now not interested into resolving all scales, we want to have a scale separation, we want to model the unresolved ones, we have to get or define some assumptions. And the first assumption would be that the unresolved scales are neglected. Therefore, the last equation will be neglected. The second assumption would be that these unresolved scales do not directly influence the larger scales. Therefore, this term disappears. And the last assumption would be that the influence of those unresolved scales onto the smaller ones has to be modeled in a very similar way as we have seen before in Rands and Alias as an Eddy Viscosity model. A very crucial point in this VMS method is the definition of this large scale space. So firstly, we define a finite element space of symmetric tensor-weighted functions. And this discrete space represents the strain rate tensor of the large scales, which can be seen here, or deformation tensor of the large scales. And there are basically two possibilities of choosing such a coarse finite element space. There is the one-level projection-based method where we use the same grid but different order, and the two-level where we have a coarse and finer grid but the same order. And in order to close also this problem, we have to define our L2 projection operator. So this one from our all resolved scale space to the large scale space. And by definition of these L2 projection operators, we can show that the differentiation commutes, which I did not mention before in classic LAS. What I think is a quite important point is that in classic LAS, in the existence of boundaries, this differentiation does not compute. So there is a kind of accommodation error, but in VMS, we do not have this error. And then the final method can be obtained. So we have our large scale space and our weak formulation. So here we have the co-projection. Since we do not want to have, we just want to have the influence of the unresolved scales on the smaller scales, and which is then with a new declared by this unresolved Eddy Viscosity. And here we also have a new constraint for the projection. In the end, I also want to show you some numerical test case, what I have realized in my master thesis. So a small benchmark where we tested or where we validate our different modeling principles, discretized with this with the HDiff conforming HEG method. Therefore, we used the turbine channel flow benchmark and define our channel flow or subdomain of size 2 × 1 × 1 with periodic boundaries in streamwise and spanwise direction, and no slip boundary conditions in X2 direction. And in order to be able to compare those setups, we have to have the same, we have to use the same flow properties. So in this case, we have always defined our friction Reynolds number, which is calculated with the friction velocity and the viscosity. And in this case, friction Reynolds number of 395 would equal a bulk Reynolds number of 13,350 with a bulk velocity of 100. The different setups I used in my validation. So firstly, for runs, we used the most, probably most sophisticated or the best model for wall-bounded turbulent flows, which is the K-omega SST model. For Alias, for VMS, we use this McQuinsky model. And for our coarse DNS or ILS approach, we used no model, but then a higher number of degrees of freedom than in Alias and VMS. And we, and all those results have then been compared to the well-resolved DNS dataset performed by Moser, Kim, and Mansour with the same friction Reynolds number. So probably the most interesting quantity is the mean streamwise velocity, so the first order statistical moment. So here the black curve, the DNS Moser is the benchmark. Then we see the green line, which is our ILS, which has a really good agreement with the benchmark. Also, the run simulation shows quite good agreement in the sublayer region and the buffer region, except here in the logarithmic region, we have some differences. And in all this also, and we can also say that the VMS method is better than the LES one. Another point we can have a look on is the turbulent kinetic energy. So in the runs case, it would be the model turbulent kinetic energy for the DNS, LES, and VMS setup. That would be the trace of the Reynolds stress tensor, or the mean of the trace. So there we see also quite good agreement of the coarse DNS setup. and the Alias is slightly better than the VMS. Also, the turbulent shear stress is quite important, since then we are able to model this part of the Reynolds shear stress sensor quite well with our RANS model, which can be seen here. So therefore, we have a good agreement. For the VMAS method, it's kind of a little bit under predicting. For the coarse DNS, we're also really good agreement, still better than the RANS model, and the Alias is quite over the benchmark. What you can have also look on is the turbulent normal stresses. That would be the diagonal components of our Reynolds stress tensor. Here the VMS has quite significant good results, better than with the coarse DNS and with the Alias. But for the X component, so U1 component, the coarse DNS shows better results. And in the end, we also can have a look at the total energy spectrum, which is quite interesting. So here we plotted our total energy spectrum in streamwise direction, so at different planes in x1 and x3 direction. So here the left one is at y plus 40, and the right one is at y plus 100. So the left one is in the buffer region, in the buffer layer region, and the y plus one is in the logarithmic region. And here we can also quite clearly see that the coarse DNS, which has the highest number of degrees of freedom, shows the probably shows the best results. So therefore, the wider range of scales is resolved. And also for the VMS and Alias, the VMS is slightly better than the Alias approach, which can be clearly seen here. But none of those simulations could resolve all scales, only also the smallest one. Yeah, thank you for your attention, and I hope you joined, and yeah, thank you.
Thank you very much, Xaver, for the nice presentation of your very nice master thesis.
Thank you.
Okay.